missions really didn't have the time resolution or the spatial resolution to study the EDR in great detail. The EDR is very small and the dynamics are very quick, so it requires a big effort to be able to study it. Now that MMS has been making observations for more than 5 years, we've found around on the order of 50 EDRs, and now have a good idea of what to look for. One key that helps us identify reconnection sites are these crescent-like shapes in the electron distribution functions. And depending on which quadrant of the reconnection site you're in, these crescent shapes take on different orientations. And so putting these electron distribution functions together and creates a map of the EDR and really paints a picture of the reconnection site and helps us study the processes that occur here. The energy, the orientation of the crescent shapes also gives us an indication of what energization processes are taking place. So after we found the first EDR, I wanted to use one of our unique instruments to study the electron dynamics in greater detail. The electron drift instrument is principally used for cross-calibration to ensure that our magnetic and electric field measurements are accurate. And to do so, it shoots an electron beam. It has a coded electron beam that is aimed perpendicular to the magnetic field. It is fired, orbits around the magnetic field and comes back to the spacecraft on the other side. And the detector on the opposite side looks for the coded message. But until it gets the coded message, it sort of it points itself perpendicular to the magnetic field and scans and moves around and around and around, looking for the beam. While it's doing so, it samples ambient electrons. So we get an idea of what is happening in Earth, in the reconnection region. And EDI does this very, very quickly. And this study was picked up in the press because we showed that essentially sometimes you got to go fast to go slow, to take paraphrase Lightning McQueen here. And so what I mean by that is, in order to really understand and study the reconnection site, and particularly the electron diffusion region, you definitely need very high time resolution measurements, which MMS provides. So if you take the circular distribution functions that I showed before and you unwrap them so that you have, basically you get these strips here where you get the number of particles at a given angle around the magnetic field. So if there's a peak somewhere in this vertical stripe, it means you have a crescent distribution present. So looking at the stripe that just before entering the the reconnection region, we see a somewhat flat distribution, indicating that there's no real sign of a crescent shape. As soon as we cross into the reconnection region, here we see a clear peak at an angle of 0 around the magnetic field, and indicating that crescents are about to form or have formed. And those crescents are visible with EDI all the way up into the EDR. And so within an EDR, we see a crescent distribution here. Whereas with the other instrument, with FPI, those circular distributions showed a clear enhancement of the crescent distribution around 60 eV. EDI measures particles at 500 eV, and particles with energies of 500 eV have a larger gyro radius. Their orbits around the magnetic field are much bigger. And so it allows you to see them farther away from the reconnection site. And so by having this large sampling rate, we're able to detect the crescent distributions, but we're also able to show that the crescent distributions are much more persistent than we had originally thought. And you can see them far away from the X-line. And that has implications for other spacecraft missions, such as Cluster, which also has an electron drift instrument. And while very few EDR studies were possible with cluster. I think maybe there's one study that I know of that claimed to be an EDR encounter. With this new discovery provided by MMS, it's possible that we can go back into the data from cluster, looking at EDI data to find even more EDRs. Another aspect of this research is enabled by the very high time resolution that EDI provides. This panel down here basically is an indicator of where we find crescent distributions. If you in the curve here, it means we have a crescent distribution. The region crescent is correlated with wave activity in the electric field. So the processes within the reconnection region that create crescent distributions so with another means of energy. High time resolution, we can look for individual wave particle correlations between the waves and the electron fluxes. And with the EDR, we look for interactions between wave and particles, and we find very coherent wave power with EDI electrons and with the electron waves. So the processes in the EDR that create the the crescent shapes also are associated with wave activity and wave particle interactions, showing a very complex set of energy dissipation processes at the heart of the EDR. So with that, I'll move on to the discussion of operations and my work using machine learning to automate our burst data management so that those tiny snippets of burst data that I just showed in the previous science results are the right data to answer our science goals. So MMS was designed to study these EDR events that occur at the magnetopause at the interface between Earth's magnetic field and Sun's magnetic field. And so it defines part of its orbit as the region of interest. It's the region where we're most likely to encounter the magnetopause. And because the electron diffusion region events occur so quickly, we have to produce a ton of data. But we can only get about 4% of all of our data to the ground for any given orbit, which means that in order to answer our science goals, we have to be picking the right 4% of data. And so that's where the scientist in the loop comes into play. The scientist in the loop is a role that passes between scientists on the MMS team. And the CITL is in charge of selecting, one of the things that the CITL is in charge of is selecting magnetopause crossings, because reconnection occurs at the magnetopause and EDRs are at the heart of the reconnection site. And so this is the type of plot that the CITL looks at. So if you think that there's a lot of information here, there is, and if you're overwhelmed by it, then it's just a small indication of what the CITL has to go through each and every time they have to look at this data. And so the MMS has an onboard algorithm to try and automatically detect different types of events that help us answer our mission goals. And the time intervals that it selects are shown in this second to last panel here. You can see it's not selecting very much, whereas the CITL selections are shown in the bottom panel, and the CITL is selecting a lot. And it goes to show the amount of time and the number of selections that the CITL has to make in any given orbit. And this is a time-consuming, arduous process, and so I would like to automate it to try and make it easier for the CITL. There are 3 methods that MMS has to select burst data, intervals for burst data downlink. 2 I've already mentioned. The ABS is the onboard automated burst system. The CITL is the human that's looking at all of our survey data, which doesn't have the time resolution required to really identify EDRs. And then there's the ground loop. The ground loop is a set of empirical or machine learning models that take all of the data that's available to the SITL, identify certain features, and pass back to the SITL to influence their selections. So today I'll be talking about my efforts to keep the SITLs from pulling out their hair and create these ground loops and automate the process. To do so, I've been awarded a NASA grant to automate the SITL selection process, and I have had three students working with me primarily over the course of this project. Colin Small has done some amazing work getting the first ground loop up and running. He's been working with the SDC to make sure that our model is in the real-time data flow, or the near real-time data flow, so that immediately when we get the data, it's run through our model and provides the selections to the SITL. He's also created the first ground loop, which is a neural network model to identify magnetopause crossings. Sam Priet was a student of mine last year now, who graduated last year. She was awarded Best Poster at the URC for her work in creating a physics-informed model to identify the magnetopause in the different regions of space that MMS encounters. Riley Powell is a student working with me now also, and he is developing a model to identify reconnection, signatures of reconnection in the data. So the first model that I'll show is our magnetopause crossing model that Colin has been working with me. This has been submitted to Frontiers and has been endorsed by both of the reviewers, so I have my fingers crossed that it'll be fully published soon. So our model for identifying magnetopause crossings is a long short-term memory recurrent neural network. And LSTMs are useful because they take time before and after the time that you're looking at to try and inform about the current prediction. This is similar to what scientists do, in that in order to really be sure you're looking at a magnetopause crossing, you can identify that before the magnetopause crossing, you're in the magnetosphere, and after the magnetopause crossing, you're in the magnetosheath. And so an LSTM does something similar. It looks at the time surrounding the point you're predicting and uses that as input. And so in training our model, we take the data that's generated is available to the SITL. We run it through our pre-processing algorithms, but we also take the input from the SITL. EVA is a tool that the SITL uses to make its selections, and for every selection that the SITL makes, they provide a text string to describe why they're making the selection. So we can filter those text strings and pick out all of the burst segments that are identified as magnetopause crossings by the SITL, and use those as our positive cases for training. And all of the other selections serve as our negative cases. So we can take the manually classified data provided by the SITL, use it for training, and create our final model. Once we have our model, we then plug it into the near real-time data flow so that as the SDC generates the data, it's passed through our model to create predictions that are stored at the SDC. So then, which is where the MMS data is stored. So then when the SITL is ready to start making selections, they log into EVA and start looking at the data, and with the data come the predicted selections that our model makes. So right now we're using our model to inform the SITL and try and ease the burden of the number of selections that they have to make. But maybe in the future we'll get to a point where we don't even need the SITL anymore. This is just five. These are three different cases of how our model's doing. The three different, all three burst selection algorithms selected similar levels. The case where the ABS didn't select anything, and one case where the GLS RLSTM model didn't select anything. So our goal is to identify the magnetopause. And so look at the ion energy spectrogram here. You can notice at the beginning of this interval, you see a high energy, low flux population and this is the magnetosphere. The lower energy, higher flux population is the magnetosheath, and the region in between is the magnetopause. So anytime you see a transition from this region to this region, is what the CITL is trying to select. And you can see this transition in the ion energy spectrogram, the electron energy spectrogram, the magnetic field, and the ion number density. So the CITL, the GLS, and the ABS all select these magnetopause crossings, but they do so in slightly different, they have different opinions on what should be selected. One key difference between the CITL and the GLS is that the CITL wants to provide context for future scientists that are trying to analyze this data. So they select the magnetopause and then select a little more on one side and a little more on the other side. Whereas the GLS has been trained to only select the magnetopause. So its selections are more honed in on just the transition across the magnetopause itself. The second orbit is a case where the ABS didn't select anything. And one of the reasons why is that the ABS was trained to identify magnetopause crossings that had also contained EDRs. And EDRs generally have a higher level of activity than do non-EDR magnetopause crossings. So here in this magnetopause crossing, there's not enough activity to really trigger a selection by the ABS. Then in this third case, the GLS didn't select anything. And one reason that we recently discovered is that our training data is all from the region of time when MMS's apogee was around 12 RE. And during that time, there was only one ROI, and MMS was pretty much skimming the magnetopause all the time within the ROI. Since then, MMS has raised its apogee to around 25 to 29 RE. And so the magnetopause is now on the inbound leg and the outbound leg of each orbit. And so we're doing really well on the inbound leg of each orbit, as I'll show in the next slide, but outbound leg, first region of interest. In the inbound leg, we're not doing so well. And so we're in the process of examining how our model was trained to try and make it better. And one last point is that each of these three intervals the selections within them were made by three different CITLs. And if you go in and look, you'll notice some key differences that are particular to each CITL. And so while there are guidelines for the CITLs to follow and what they should select, there's some freedom within those guidelines so that each individual CITL has its own sort of opinion on what should be selected and how to select it. In that sense, the GLS and the ABS serve as co-CITLs that also have their own opinion of what should be selected, and hopefully between the three of them, we get everything that we need. So looking at all the selections that we've made over the 5 months that the model has been in operation, we can first make a comparison between the CITL, the ABS, and the GLS for all selections made by the CITL to see what the overlap in their selections are. And it turns out that the CITL is selecting a very large portion of the GLS and ABS selections, meaning all of the selections that the GLS and ABS are making are of interest to the CITL. If we go and look at only the magnetopause crossings, we see that the GLS is selecting a very large number of the time intervals that are indicated as magnetopause crossings by the CITL. So it's doing a very good job of identifying magnetopause crossings. However, the ABS is not doing a good job as well of a job at identifying magnetopause crossings. The good thing is that because there's also very little overlap between the ABS and GLS. So well, the good thing is that ABS and GLS are of interest to the CITL, and there's very little overlap between them, meaning that they're complementary systems. So they're both selecting different things, but those things are very relevant to the mission goals of MMS. So where are we going with all this? What is the plan now that we have our first ground loop? How can we build the ground loop infrastructure so that we can take over more of the tasks that the CITL has? Our plan, or my vision for this, is to create region identifiers. So create an identifier that can pick out data from the solar wind, magnetosheath, and magnetosphere. And that way, when you go to create your event identifiers, for example, if you're looking at hot flow anomalies or slams, which are only found in the solar wind, you don't have to train your model so that it knows what magnetosheath and magnetosphere look like. You can just have a specific model looking at solar wind data to identify slams and hot flow anomalies. This follows a trend in industry that has demonstrated that a large number of very specific models does a better job than one do-everything model. So once we build up this infrastructure of event detectors, we can start pairing them up to build science campaigns. So a few studies from MMS have shown that microinjections, or very, very short bursty intervals of high energy particles, are associated with low frequency wave activity in the form of field line residences. And that those field line residences are associated with Kelvin-Helmholtz waves at the magnetopause. So this large system of events has to be well understood in order to really capture the physics involved in this process. So we can activate the machine learning models specific for each of these events and create a science campaign out of it. So not only are we automating the CITL process, we can now start automating some of the science discovery process as well. So that leads into the next machine learning model, which captures region identification. So trying to build up the infrastructure to identify the regions that can then be passed to the individual event identifiers. We do this with a physics-informed approach. And so neural network models are somewhat notorious for not being easily interpreted. Our approach with this model is to sort of mimic what we do as scientists to identify each of these regions. And I'll go through each aspect of this in turn. The first is we're trying to figure out what do the regions look like. And so this is the same CITL plot as before, and I've went through this exercise of identifying the magnetosphere as this high energy, low flux region, and the magnetosheath as the lower energy, high flux region, and these intervals in between as the magnetopause crossings that the CITL is selecting. So just in these 5 to 10 seconds, I've taught you how to identify magnetopause crossings in our data. And we're able to do that so quickly because our eyes don't look at each individual points. Instead, we look at the collective of points and create sort of a distribution or a concept of what each of these regions look like. So that's what we want to build into our model. We want to build in the concept of what is the magnetosphere, what is the magnetosheath. And to do that, we can just throw all of our data together, and because the data from each region looks differently, it'll cluster together in different regions of our graph. And we can use expectation maximization to figure out which population each individual point belongs to. So given a new data point, what is the expectation that we're within 1 standard deviation of the mean of either of these distributions? And so we use this expectation maximization to fit our distributions, to create fits of Gaussian distributions that tell us basically what the probability of being in the magnetosheath and magnetosphere is. So then once we have them, any new point y can be modeled as a superposition of our magnetosphere distribution and our magnetosheath distribution. And the likelihood that this new point belongs to the magnetosheath is 1 if it's from the magnetosheath distribution, and the likelihood that it's from the magnetosphere is 1 if it fits nicely within our magnetosphere distribution. And to obtain this likelihood function, we can use Bayesian inference. Bayesian inference basically takes our prior distribution, which is our concept of what the magnetosheath and magnetosphere looks like, what we gathered from our expectation maximization. And it tells us the likelihood that any new point will falls into our prior distributions. We can combine our likelihood function and our prior distribution to update our knowledge, update our concept of what the magnetosphere and magnetosheath look like, and that's our posterior distribution. So our new data point is representative of our posterior distribution, and we have our prior distributions from binning all this CITL data together. Now we want to find out what the likelihood is that we're in the magnetosheath or magnetosphere. So we can do that. So we'll use that to figure out what the likelihood is. Now, one thing about the data is that you can't just randomly jump from the magnetosheath to the magnetosheath and back. There's some value of inertia. So if you take any given data point and plot it against the next data point in time, you get this nice linear distribution. And that means that time points that are close to each other are related to each other. And so it's not just, you can't just encounter random values and jump back and forth from the magnetosheath to the magnetosphere. So we want to build this inertia into our model. And so we figure out how far away from the time point that we're analyzing do you have to get before your distribution of points is truly random. And that represents sort of the inertia of transitioning from the magnetosphere to the magnetosheath. But our data isn't labeled as being the magnetosphere or the magnetosheath, so we have to come up with what these labels are. And to do that, we can use hidden Markov models. As a analogy of what we're trying to do, you can imagine yourself being in an office with no windows. And you're getting hungry and you want to go out to lunch, and you want to know if you need to bring your jacket and your umbrella with you. But because there are no windows in the office, you can't really tell. So you go to your balcony and you start watching people come in from outside. And if they're wearing dresses, short sleeves, shorts, things like that, you know that you can leave your jacket inside, you can leave your umbrella inside, and you can go out. It's a nice day outside. So based on the observed data, we can label our hidden variable as the weather as being hot, cold, mild, rainy, whatever. And in a similar manner, our data is everything that the CITL is looking at. And from that, we have to infer the label given to it. Where are we? The magnetosphere, the magnetosheath, the magnetopause, or what? And our hidden Markov model will help us with that. And so once we have our likelihood functions, we get a single likelihood function for all of the variables that the CITL is looking at. And if you think back to elementary school, where you have to take your graphing paper and plot each individual point on a graph, and then take a ruler and draw a best fit line through it. That's essentially what we're doing to create a single predictor, a single indicator of where we are in space. So all of these lines here represent our likelihood functions for each individual variable. And from this, we want to create a single predictor of whether or not we're at the magnetopause. And this best fit weights each of these variables and tells us which variable is most important for determining, is the best identifier of each region of space that we're looking at. And so putting everything together, we try and figure out what the regions look like, what the likelihood is that we're in a given region using a given number of variables, and then combining all of those variables together to create a physics-informed model that tells us where we are in space. So how are we doing with this? Of all that we've tested this on, our true positive rate on a point-by-point comparison is 66%. So not doing quite as well as the neural network model, but a caveat with that is that time series data, as I showed with sort of the inertial effect of not being able to jump randomly from one point to another, and also with the CITL, in that the CITL selects a wider region of a wider time interval than the LSTM model did, because it's trying to select more context. So it'd be more fair to make a comparison on a selection by selection basis to account for the partial or multiple overlaps between selections. And that's something that we're working on, but 66% still isn't that bad. And our true negative rate, our ability to reject selections that were not selected by the CITL, is very high at 90% roughly. All right, so that wraps up my discussion of machine learning and operations. Now I'll get into some of my efforts to instrumentation for future missions. This involves a Rogowski coil, a Faraday rotation emitter, and a racetrack magnetometer. And for this, I've relied, again, pretty heavily on student support. Joe Lazaro, Jonathan Amrian, and Jesse Greenhalgh have been working with me on the Rogowski coil design. Jonathan had a summer undergraduate research fellowship with me, and he helped design the mechanical aspects of the instrument. Jesse created a very nice numerical model, and Joe was working on the electrical design. For the Faraday rotation emitter, Jason Sisk has been with me for a while and has maybe shown more loyalty than I may be deserving of. He got his bachelor's degree with me in 2008, trying to modernize the Faraday rotation emitter, and is working on his master's degree with me now to sort of improve the detector electronics for it. So this is a picture of our Rogowski coil, our prototype design. AC currents that pass through the center of the instrument can be picked up by the permeable material in here. And that in turn induces another current in the copper windings that can be read and digitized and used as data. This instrument is scheduled to fly on the ACES-2 sounding rocket. And ACES-2 is trying to study current closure by looking at, it has two rockets, one for the current closure region to look at perpendicular, and one high above that region to see what the electromagnetic inputs are to the current closure and field-aligned currents.
I'm sorry, excuse me, what you just said got totally broken up. I don't know if anyone else could hear about the two rockets.
Okay, the is studying currents in the current closure region, trying to identify perpendicular currents, whereas the rocket with the is looking at the inputs to the current closure region, so the electromagnetic inputs and the field-aligned currents that feed into it. The next instrument is the Faraday rotation ammeter, which also measures electrical currents, but is able to measure DC currents, whereas the Rogowski coil only measures AC currents. The Rogowski coil is primarily made up of a very long, or I guess a loop of optical fiber that is very long if you unroll the loop. Current passing through the loop causes Faraday rotation in the laser light that is input into the fiber optic cable. The input polarized beam is compared to the output polarized beam, and the angle of Faraday, the amount of Faraday rotation is proportional to the current, which gives us a measure of the current density. And my current efforts, Jason and I are writing a proposal for the heliophysics technology and instrument development, which needs to be submitted in a little over a month, and hopefully get funding for this. And there are several applications for this. Similar to the Rogowski coil, it can be flown on a satellite or on a sounding rocket to measure field-aligned currents or any type of current system. It can also be installed as a ground station. As I mentioned in the beginning of the talk, the geomagnetic activity of these substorms can produce very strong currents in the ionosphere that are picked up by power companies in the form of geometrically induced currents. And those can lead to power disruptions. But the industry doesn't want to release that type of data because it makes them look bad. And so we have to make inferences about these GICs. With the Faraday rotation ammeter, we can get more direct knowledge about the GICs that are happening. Finally, the Racetrack Magnetometer was currently funded to fly on the solar wind follow-on mission. The Racetrack Magnetometer is unique in that it has a racetrack shape, and this helps lower the noise floor from typical ring-shaped magnetometers that are more of a circle rather than a racetrack. And so the current progress on this is that we have a rolling mill and we have the highly permeable material that is at the heart of these instruments. And I've been the material so that it's 100 microns thick. And this is the mill, this is the material, this is the before and the after. I have I guess I can pull out a prop and show the mill process that I captured with my cell phone here. So I just put in the material, roll it through, pass it through time after time after time. And then once it's thin enough, I send it off to a photo fabrication laboratory to have these racetrack shapes etched out of it. So that's what we're trying to do currently. The solar wind follow-on mission is one that'll fly to the Earth's Sun Lagrange point here and act as a space weather monitor for NOAA. So NOAA will take our data as real-time inputs to their machine learning and numerical models to try to provide predictions and space weather forecasting to industry and public and private partners. So that wraps up the pillars of my work for space weather mission design. Now I'll wrap things up and discuss some ongoing research that I have. So on the science side of things, I talked about my work with EDI and how we used its high time resolution to study crescent shapes and show that as long as you know what you're looking for, you don't have to be within the EDR to sort of sound the EDR to know that it's nearby. And this has implications for other spacecraft like Cluster, which has an EDI instrument and may be able to now go back and re-examine its data and find these EDRs. We also showed that the crescents that developed within the EDR are associated with wave activity and wave particle interactions that may be another source of energy transfer and energetic particle production. On the operations side of things, I used machine learning to implement the first machine learning ground loop into the MMS data stream to try and automate some of the signal selection process. I've also created a region detector that will enable a hierarchy of ground loops and hopefully not only automate the event detection and signal processes, but also help us with science discovery and any science campaign that the mission may have in the future. For instrumentation, I have the Rogowski Coil, the Faraday rotation ammeter, and the Racetrack Magnetometer. The Rogowski Coil and the FRA can be used to study field-aligned currents and clearance closure and magnetosphere-ionosphere coupling. And the FRA can also be used to look at GICs and get a better understanding of how our electrical grid infrastructure is being affected by geomagnetic activity. The Racetrack Magnetometer is being flown on the solar wind follow-on mission and will be used for space weather forecasting and operations. And I've been working with 7 undergraduates and one graduate student. I'm really happy with the work that I've been able to do and really grateful for what they've enabled me to do in my career. And so my vision for the future, some immediate things that I'm a part of, there are two mid-X's that are currently under evaluation, Helioswarm and OMIC, that I'm a part of. I'm also a part of an up-and-coming SMEX mission and have a rocket mission of my own that I'm trying to push forward. On the science side of things, I process all of the level 2 data, the science quality data for the EDI instrument. I also process data for the magnetometers, creating a magnetic field data product that has the whole spectrum of magnetic field activity. So combining our 2 magnetometer instruments into a single data set. I'd like to unite my science for those two instruments to study turbulence within reconnection, and particularly see if there's any sort of statistical scaling law associated with turbulence and energy dissipation. For machine learning, I'd like to combine my work with EDI with machine learning to create an emulator that will basically emulate the observations made by EDI, so that even when EDI is off, our emulator can produce measurements that are representative of the instrument itself. And with that, we can create a global machine learning model of the intermagnetospheric magnetic electric field that can be used as inputs into numerical models. And part of my machine learning efforts are being highlighted at this year's virtual GEM conference next week. I'm chairing a session with a few other people to try and assess the state of machine learning in GEM and raise awareness of the different activities that are going on. So that's my work, and thanks for listening.
All right, thank you very much. I'll applaud for everyone. So do we have questions? If you want to raise your hand. I see Aberhart there.
Let me unmute here. So I enjoyed that greatly. There was a great presentation, and it looks like with a great vision. I have a question on your operations part. So you talked about how with machine learning, you can identify various structures, regions, and processes, process regions. Yeah. And you showed the percentages of positive identification. But I'm wondering, often you are dealing then with false positives, and they can distract from the success of this. And I'm wondering, what's the probability that you are getting false positives? What are potential consequences, and what would you do about that within your machine learning?
Yeah, so for MMS in particular, false positives can be an issue because we get so little of our data to the ground that false positives can sort of pollute the data that is stored on board for downlink. And so that has to be taken care of. That has to be considered during the design process. And luckily, much before I became involved with MMS, there were lots of good people working on that. And they have enough memory on board and enough capability to accept a certain number of false positives. And so what I didn't show is that there's a receiver operator curve that basically lets you set your threshold of how many true positives and how many false positives you're willing to accept. And so we can tune our model to make that threshold be acceptable to our mission standards.
Okay, yeah, thank you. That sounds like an appropriate approach there. And but I can imagine there's a lot still to do towards the machine learning, and the more complex the missions become, the more important this will be.
Mm-hmm. Yep.
Are there other questions? I'm not seeing any more hands. I had a question. I didn't quite get your last. You said that you were going to be emulating the measurements of EDI and then using emulated measurements to make a model. Is that what you said? I didn't understand that.
So part of making the model is using EDI electric field measurements and our double probe electric field measurements. And a statistical model, a sort of a static non-machine learning model has been created. And that just assumed that EDI was correct. And then whenever we didn't have EDI data, EDP data could be used. And so the emulator will be a means of evaluating just how well EDI is doing, and so that we have a better means of assessing the data that is being input into the model.
I see. So it doesn't mean you can get rid of EDI. It means that you're better assessing when EDI is giving good measurements. Is that
right? Right.
Okay.
And hopefully to help assess the EDP measurements when EDI is not operating. But we still have to determine how that works.
Okay. Reka, you have a question?
Yeah, just wanted to say, Matt, this was a really great talk and really neat neat work that you've done. I really wish that I would have had some of this experience back in the messenger mission when I had to identify thousands of magnetopause crossings, which was not fun by AI and by hand. But I might reach out to you in the next little while. Is preparing for the Bepi Colombo mission to Mercury to do something similar for identifying magnetopause crossings.
That'd be great.
Thanks for the talk.
Anyone else? I have one more. So I think Cluster also did some kind of region identification that's part of on their science site. You can pull things down by region. Did you check what they did and compare it with what you?
I know, I'm aware of one model by Yuri Kyotsintsev group at IWF that has done something recently. They've also applied it to MMS data. Where one of our next steps for this is to do model validation, and so we'll be comparing their model with our model.
Okay. And Kevin has a question.
Hey Matt. Yeah, I had a question. Would it be straightforward to apply this model to, say, for instance, cluster data? Does it matter which mission collected the data, or is the model just a sort of universal tool for identifying magnetopauses?
Right. The neural network model, the LSTM model, is probably more sensitive to instrument characteristics such as noise and offsets. So one thing that I've wanted to do is all of our models are publicly available, and we have notebooks to run the model. We have notebooks to reproduce all of the plots in the paper that we just wrote. So all of our stuff should be easily to use. And so I would like to take our notebook and adapt it for cluster data to see exactly how well it does. So the neural network, I expect to be more picky about the quality of data that is given to it, or the type of data that's given to it. The physics-informed model, however, I expect to be more general. And I have a feeling, without having any experience doing it, I have a feeling that the physics-informed model will be able to be used across missions.
Thanks.
Yeah.
All right. Are there any other questions? If not, we can thank our speaker again and go about our day. Thanks very much, Matt.
Yeah, thank you. Thanks everyone for listening.
Thanks, Matt. Thank you, Matt.
Thank you.
Matt. Thanks.
Thanks, Matt.
Thanks, Matt. Thank you, Matt.
Bye.
Bye.
Thanks, Matt. Hey, I have one more question for you. Do you have any idea how to save a video on Zoom?
I think
No.
Does it automatically do it?
it must automatically do it once you've hit recording, then
Okay.
you stop or whatever.
I'll clip this part out of the recording.